All right, so today I'm going to be talking about, let me actually try to get the screen sharing going here. Today we're going to be talking about signal to noise, and hopefully you didn't all happen to see the talk at OPT that I did on this a couple of months or so ago. If it is, well, be prepared for about the same talk. Um, but we're going to be talking about signal to noise because in terms of coming up with your final image, the kind of image that you want to send on off to, astronomy or sky and telescope or put up for an APOD or even just share with your friends, signal to noise really is it. If you don't have it at the beginning, you're not going to be able to have it at the end. So there's a phrase often in computer science called garbage in, garbage out. And well, that's really what we're going to be talking a lot about here today. So as a bit of an overview, going to be talking about what is signal to noise and why you actually should care about it, and then also talk a good bit about the kinds of things that you can actually be doing to try to improve your signal to noise and make cleaner looking images. Because if we really think about what it is that's going on here when we take our images, I mean, you open up your camera, you've got a telescope hooked up to it, and each pixel covers a little tiny swath of sky. Maybe it's an arc second by an arc second worth of sky, maybe it's 3 arc seconds by 3 arc seconds, but no matter what, you're covering some portion of the sky with every pixel. Your goal then in making this image is to actually figure out the intensity at every given pixel, so that as we move across the image from pixel to pixel here, we're moving across our target, and your goal is to come up with the actual intensity at that spot. So in the end, you have an image that's actually the target. So if we just take a look on the bottom here, this word signal. Okay, well, there we have a nice big bright set of letters on a black background. And if we took our images, and if every first image that we took looked like this, the signal nebula here, that would be one thing, but that's not what it looks like. When you take your images actually look much more like the things that we see on the bottom here. We have still this signal, we have this image, these white letters, but now it's embedded in a bunch of noise. And our goal, though, when we're taking our images and when we're processing our images, our goal is to try to get as close as possible to that original image. There really is some flux of photons we're capturing from a galaxy. And if you move over a little bit in the sky, maybe you're in a dust lane, so you're getting fewer photons from that galaxy. Move over again, you're outside of the dust lane, and now you should be getting some more photons. So what we really want to try to do is come up with our best estimate. You will never have the exact right number of photons. You are always going to have noise in your image. The trick then is to figure out how do we have the best signal to noise, the best ratio of how much signal are we actually having relative to how much noise. All right, so I've been talking about signals, I've been talking about noise and signal to noise. What the heck actually are these things? Well, signals, we have signals that we care about, and those are photons actually coming from our deep space object, our DSO here. So those are the things actually being emitted by stars in the galaxy or this sort of thing. We also have signals that are things that we don't actually care about, but it really is signal. I mean, and this is going to be a very important point to understand what is signal and what is noise. The glow coming from the sky, those are still photons. Those are photons. They've been emitted by things like streetlights. They bounce up off the sky. They come back down. They hit our detectors. But they're photons, and they're just really the same kinds of photons that are actually making it from that galaxy far away. So we have sky glow. You have dark current, which is just, well, photons up in infrared that are then getting into those CCD wells. That's really all dark current is. And each of these is going to be building up at some particular rate. So you open up the shutter and you're going to get a photon every second from that DSO. You may get 5 photons every second from your sky glow, whatever. But you're building up those photons. The noise component, however, is our random factor. So we have a number of different kinds of noise, number of different flavors of noise. One of them is that every time you read off an image, every time those photons get converted into electrons and you send them into the readout registers on your CCD, whenever you do this, there is some amount of just inherent randomness that is added in. It's called read noise. Different cameras have different amounts of read noise, and this is the noise inside your electronics. We also, though, have shot noise. Shot noise is a kind of noise that comes in anytime you're having a signal from photons here. You're going to have shot noise. It's also sometimes called photon noise. And this comes about because the actual emitting of photons that comes off doesn't happen at an absolutely perfectly smooth rate. There is some jitter, some randomness to this. There's an expected value. On average, they may come in once a second, but sometimes it'll be a second and a half, maybe then it's a half a second, maybe then it's 3 seconds, then it's a quarter of a second and a second and a quarter. But there's some randomness actually to that. And so therefore, if you opened up and you took 10 seconds worth of imaging, you wouldn't be assured you would have exactly 10 photons that you captured. There's this randomness. It follows something called a Poisson distribution. And it comes about, here's a little like odd side note here, Henri Poisson, who figured all this out. He figured it out not having to do with photons or electrons or anything like this. He was a surgeon and a mathematician in the French army. And this was back in the day when, well, there were things like cavalry. And he would find that, you know, sometimes he'd, well, get somebody kicked by a horse, and it'd just be another day before somebody else was kicked by a horse. Sometimes it might be 3 or 4 days. Sometimes you'd have 2 people in the same day who are kicked by a horse. And so I guess just sitting there on the battlefield, a little bit bored or whatever, he tried to figure out, okay, so what's the distribution? How does this kind of thing behave? And whether it's people getting kicked by horses in battle, or whether it's photons actually coming out and capturing your CCD detector, they follow this same style of random process. That's a Poisson distribution, whereas read noise follows this pretty Gaussian distribution. And Gaussian is your bell curve, your normal distribution. Okay, so signal-to-noise ratio, or SNR, is just how much signal do you have divided by how much noise do you have. So it's the amount of signal over the amount of noise. So if you're in your image, you know that you stick your cursor over and you see, hey, look, I've got 1,000 intensity units here. Okay, that is your signal plus your noise. Maybe you could actually figure out that really 990 of them came from signal and 10 of them came from noise. So then your signal to noise would be 990 over 10, or 99. That's all it is. It's just simple division here. Okay, so what does this look like in an image, and why should you actually care? Well, hopefully you can see on the screen now a nice image from Warren Keller. I downloaded off of his website. And it's a pretty image here of a nice galaxy, and you can see, you know, I would be very happy to be able to call this my image. All right, this has got a pretty nice high signal to noise. We can degrade Warren's image and make it look like this. Hopefully you were able to see that, yeah, you know, that doesn't look as good. There clearly now is some more noise, particularly in the background, you can see here. And so if I were to try to think, okay, am I going to send some picture off to, you know, to a magazine or to a friend, I'd be much more likely to do it with this one than with this one. This is why we really care about signal to noise. The only difference between these two images, the only one at all, is the signal to noise ratio. So when you're looking at your images and you're trying to pull out that extra little wispy bit of nebula, that extra arm in the galaxy, when you want your background to be nice and smooth, all of these depend on the signal to noise. You know as you're stretching your image that it starts to go to pot at some point here. And that's when you stop stretching and pulling anything else out. You've hit your noise floor. You've hit the level at which you are now down in the noise and there's nothing left that you're going to be able to pull out. All right. If the arm of that galaxy is inside that noise, you're out of luck. So that's why we really think about garbage in, garbage out, and what we can actually do to try to boost up and maximize the signal to noise actually in our images here. All right, so here's another image just showing two different signal to noise ratios here. And we also have the actual equation for the full signal to noise in our images, or at least it's a pretty reasonable version of the full equation here. So what we have on here, signal to noise, you remember, is the signal over the noise. And so we have our target signal on top. The noise comes from a whole bunch of different sources. Remember on that slide before, I already talked about different sources of noise, and one of them is the read noise. That's the far right-hand side of this equation here on the bottom there. Each one of the other sources of photons, though, had its own shot noise. So your target signal, the actual photons you're getting, remember there's a random jitter to the pace of the photons there, and so there's going to be a noise associated with that. Same with the sky glow, same with the dark signal. So you have to add all of these noises up, and they add in this geometric mean kind of thing here, where you sum them up, you take the square root of them, add all of those up, and then that is your total noise in the image. Now, as you're going through and as you're trying to figure out what you can actually do in this, what we're going to be able to do is we're going to be able to do things that's going to be able to boost our target signal, and we're going to be able to do things that will reduce our noise, but I want it to be clear that there's nothing you can really do. You can't subtract the noise from an image. You can't subtract the noise because you don't know what the noise is. Remember I said before that if you had your cursor hover over a pixel and it came up with a value of 1,000, how do you know how much of that 1,000 came from the actual DSO and how much came from the noise? So without that, without knowing ahead of time how much came from each, you're never going to be able to do the subtraction. You could know on average how much noise there might be, but the whole point of it being noise is that you don't really know. If I were to take a coin and say, all right, I'm going to flip this coin, and I want to figure out what are the odds of heads and the odds of tails. You know, if I don't know ahead of time that it's 50-50 and I just flip it a couple of times here, I'm going to get, well, maybe 2 heads and 1 tail. So I might think it's 60%. All right, well, okay, I can keep flipping it and flipping it and flipping, and then eventually it'll come out that it's pretty darn close to 50-50. Maybe after 1 billion times it'll be evenly 50-50. But the problem is on any given sample, I'm still not going to know what that was. Should I have taken out a head or should I have taken out a tail? And so let's say my coin really is weighted and it's not actually 50-50, or I say, okay, look, I'm gonna cheat, and sometimes I'm gonna flip a coin naturally, and other times I'm gonna fake you out here, and I'm always gonna get a head. And so we add all of these things up, and so on average, it's 60% of the time I'm getting heads, and 10% of the time, and 40% of the time I'm getting tails. In any one sample here, I don't know. Was it an even flip? Was it actually one of those times where I embedded something in there? You don't know, and that's the problem. In this case here, the cheating is, well, okay, what's the value of that pixel? And a bunch of that value comes from the DSO itself. All right, so here what we have is, you know, I've shown these two images here, and one of the things that I want you to know is that, take a look at this, is anything you can do to boost your target signal here is going to be boosting your SNR, straight up. You double the target signal here, you are going to be boosting up the noise. It won't be exactly doubling it because that target signal has its own noise component with it. But if you do something like you say, okay, hey, if let's do an easier one here. If my target signal goes up by a factor of 4, well, the noise component from that target signal is going to go up by the square root of 4, or by 2. So then my signal to noise went up by 4 over 2, or my signal to noise doubled. So anything we're going to be able to do to boost up our signal is going to be a nice big thing for us. So how do we actually boost our signal to noise ratio and get these cleaner images? Well, I've already given you the 2 answers here. One of them is you boost your signal, and the other one is you reduce your noise. Okay, so we're done, and we can pack up and take questions. All right, no, we're not quite done actually yet. Let's actually talk about these kinds of things and practically what you can do, other than the smarmy answer of just saying, well, just go fix it. So how do we actually boost this? How can we start to pick this kind of thing up here? Well, one thing that you can do is you can say, all right, we are going to just add more images. So if each time here, if I take an image, I get 1,000 units or so out of the DSO. I add another one. I'm at 2,000. I add another one. I'm at 3,000. I'm at 4,000. I'm at 5,000. And if we do this, we are then boosting up our signal. Of course, at the same time, we're also inducing noise. Each one of these has a noise component with it. But remember that signal goes up with each one you add in, and the noise goes up by the square root of that. So your noise then is going down by a square root of the number of samples. Now, if you take a look and you just sort of plot this curve, if you say, okay, look, how much noise is there in a stack of images relative to a single image, we can see then that as you add in more and more images, it follows this decaying curve. This is a 1 over root n curve, or 1 over the square root of the number of samples. So in the very beginning with just one, yeah, you got a whole bunch of noise in there. As you go and you add another one, it's root 2 that. You keep going and you keep going and you keep going, and what you can see then is that this flattens out. This is why some people give recommendations of things like, don't bother taking more than 20 images or 30 images or 40 images or something like this. Because if you look at here, the big divisions are every 5 images. So we can see after 10 images, you've cut your noise massively from a single one. All right, well, after 20, you've cut it again, but the percentage improvement that you've had here, or the total, sorry, I should say, the total amount of noise that you've dropped is less. There is a point of diminishing returns here. And so at that point, once you've done things like you've said, okay, look, I've got 10 images, is taking an 11th image really worth it? No. The difference between 10 and 11 is not all that big. You want another big chunk? All right, get to 20 images. You want another big chunk? Double it, get to 40 images. All right, so that's the way you've got to really be thinking about this kind of thing. So if you're sitting here and you're saying, well, I took 70 images and I was really bummed that I didn't make it up to 80, stop worrying about it. There's not really going to be much of a difference between 70 and 80, but there still is a difference between 20 and 70. All right, so when we take a look at what this actually looks like, we can see this kind of thing here. To put it visually for people instead of just a graph, here's this same Rosette Nebula image. It's actually a frame of mine. And I said, okay, look, here's one version of it. What happens when you stack 10 of them, and then what happens when you stack 100 of them. And the relative noise values, I made up an arbitrary number here of noise in the first one, but you can see that this noise then goes down with 1 over root n. Okay, so that's the first way that you can actually be boosting your signal to noise, and one that we all know about here, but that's why it actually works. Next kind of thing that we can do is we can say, all right, instead, or in addition, let's expose for longer. Now, I happen to put up a image here from Steve Canistra. There are a number of different calculators you can find on the web for the signal to noise series that I did on cloudy nights a number of years ago. I've got one. It's a simple Excel spreadsheet that you can download and use in Excel or OpenOffice or whatever. In any case, they all do the same math, and it really doesn't matter whose calculator you use. They may factor in slightly different components or something, but you're going to end up with the same shape of the curve, which is really what I want the take-home here to be. So what this is showing is this is saying, okay, if you are going to have a total exposure time, you're saying, I've got an hour for my red channel, or I've got 2 hours for my luminance channel, or whatever it is, how do you divide up that hour? Should you take 5-minute shots? Should you take 1-minute shots? 10-second shots? Hey, why don't we just take 1-second shots, because my mount can track for a second just fine. And I'm going to stack a huge number of 1-second shots on top of each other, and I'm going to be in great shape. Well, no, you're not going to be in great shape, and that's the purpose of this curve here. So this is saying, given a total, say, of an hour or whatever of total exposure time, sorry, 4 hours in this case here, what does it look like if you divvy it up into these different lengths of subexposures? So you can see here it's getting this same kind of curve. It's a mirror image from the previous one, but you can see this same sort of shape, such that if you use very short exposures, your signal to noise is pretty poor. And as you lengthen it up to a minute, you've gotten much higher in your signal to noise. In this case, it's at this level of 18. You get up to 2 minutes, and now you're up at around 22 or so. You get up to 5 minutes, and here you're pushing 25 and a half. You get up to 8 minutes, or even 6 minutes or so here, 6, 7 minutes or whatever. You're up to a signal to noise of 26. So that's why this is highlighted in the red band. Avoid this if you can. Okay, at the very least, try to hit this. All right, now here's a sort of a meat where you can try to get into. And again, you hit this point of diminishing returns. Do you really want to leave the shutter open for 30 minutes? Yeah, your signal to noise is going to be a little bit better than if you leave it open for 10 minutes. Not much. Maybe 26 and a half versus 27. Not a gigantic thing. And if you've done that, you've opened up the chances for your mount to have some kind of error. Maybe the wind blows. Maybe you hit a bad spot on your worm. Maybe a satellite or a plane goes through the image. Personally, I'd rather take, say, 5-minute exposures or 10-minute exposures and have to throw away one of them and lose 5 minutes worth of data than have to throw away 30 minutes worth of data. Okay, so that's why that's sort of the shape of this curve, but why does the curve actually look this way? What's really driving this? Well, if we think about this, if you double the exposure here, you're getting 2 times as many photons from your deep space object. That's good. You've doubled the DSO signal. You get still one shot of the read noise, one element, I should say, of the read noise, just to not use that term there, instead of 2 of them. You get twice your sky glow, and you get twice your dark current. But this noise component, again, is in this square root term. And so since we've done this kind of thing and the noise is going into this square root term, again, you're getting a 41% boost, a root 2 kind of boost by doubling the exposure. Quadruple the exposure, and it's doubling. But that's, again, you have to think in terms of these doublings and quadruplings to then have this. And then that's why if it's like, okay, I'm at 10 minutes, I need to quadruple the exposure to, okay, I'm not going to really get into that. Okay, so we can see these kinds of things, that why you get these curves to fall out this way. Other things that you can actually do in terms of actually sort of boosting the amount of signal here is you can decide, all right, you know what, I want to have more photons actually coming in to my pixel. Be a nice thing. If you sort of turn up the volume here on the galaxy, you'd get more photons coming up. We're not going to be able to do that. And so one of the instincts that people have at this point is say, well, look, you know what, I'm going to have to just get a bigger scope. I've been using my little 4-inch scope or something like this, and, you know, Palomar is huge and Hubble is huge in comparison, so I've got to get a bigger scope to be able to do it. No. What you need to do is you need to actually change the F ratio of your scope. You can do that by boosting up the size of your telescope, but only if you keep the focal length constant. Or you can reduce the focal length for your given object. So this is something that for a while was very, very hotly debated on the internet as to exactly what F ratio is doing when it comes to the signal to noise in your image. When it comes down to thinking of the signal to noise at the level of a pixel, how well are you estimating the actual brightness in the sky for that spot in the sky? Signal to noise, perfectly, when you're talking about that kind of signal to noise, the F ratio very, very beautifully describes your signal to noise. The F ratio is describing how much of the sky you are actually having be subtended by not only your entire sensor, but also by every little pixel here. And so if you go from a, say, like a 560 millimeter focal length scope, 4-inch scope here, so it's an f5.6, if you drop that down to an f4, you just go from f5.6 to f4, keeping the aperture constant, you now have doubled the amount of target signal that you're actually getting here. So you've boosted that up. Yeah, you've boosted the sky glow and everything in it. But again, it's another one of these times then where you are boosting your signal to noise by 40%. Personally, I would take 40% any day of the week. Okay, let me step through this just to make sure that everybody gets it, because the other thing that's sometimes said is that, well, hey, look, I can grab a little SLR lens, a 50 millimeter SLR lens, and slap it on my telescope, and it runs at f4, and Palomar runs at f4, so they do the same thing, right? Well, no, they don't do the same thing. They're going to have very different magnifications. But the brightness, the amount of sky that you're covering for each thing is then going to end up being the same if you keep the aperture there constant. So F ratio is really just, the mathematical definition is it's the focal length divided by the aperture. So we can think of this triangle that we have here, where we see that the aperture is the left-right portion of the triangle, and I can't seem to get my cursor back here. The aperture is the left-right portion of the triangle, and the focal length is the height of the triangle. And so the F ratio is then just this ratio. If we reduce the focal length of the scope, but we keep the same aperture, okay, we now have a much more squat triangle here. So we've dropped the F ratio. If you say, okay, look, I'm going to keep the same height of that, but instead now I'm going to say, okay, I'm going to stretch the aperture, I'm going to increase the aperture. Again, we get that same squat triangle. And that squatness of that triangle, that's really saying how wide of a swath of sky either is my entire sensor or is every single individual pixel covering. That's what's so cool about the F ratio here. It's describing really the field of view, the width of the sky, that angle that you're actually getting each pixel to cover. And that's why then changing that means that you're going to be getting more signal coming into it, assuming that you're not at the point where you're actually, if you're doing things like dropping the focal length, you're obviously changing the image scale. And that, of course, is the huge difference between something like, Palomar and your f4 SLR lens kind of thing. At f4, Palomar has a much, much, much greater magnification. So that's why, that's really the point of going up to a big aperture telescope, is to be able to get those increases in magnification. So in all of this here then, really as we're thinking about F ratio, what you want to think about is how much sky do I really want to cover? What kind of sampling do I want to have in terms of the resolution in the image I want to have? And in all of that then say, you know what, if I want to pull out these faint fuzzies, these great extended objects like DSOs, I really want to try to be as at low a focal ratio as I can. Okay, so for those of you who then still are saying, hey, I don't know, this doesn't make sense, or I don't believe it, or what have you, let's just stick an image up here. It's the same setup. We're taking the same exact night on the same exact camera using two different telescopes. On the top, this was an 8-inch f5.75. It was a Newtonian being run with a paracore there. That's why you get a little bit of an odd number. Had nice high reflectivity mirrors and all this kind of thing. And on the bottom is a 4-inch f4 refractor. Now then, which one of these has a higher signal to noise? I mean, the 4-inch f4 refractor is overall grabbing 25% as many photons from the sky because it's a smaller bucket. It's a smaller aperture, letting fewer photons through. But it's packing those fewer photons. It's taking the swath of sky and then packing more sky onto each one of the pixels. So despite spotting the 8-inch telescope here, all of those photons, 3 out of every 4 photons, it's thrown away because they're never even making it inside the lens. Despite that here, it's less noisy. In the end, you're getting almost 3 times as many photons per pixel on the small 4-inch scope as you are on the 8-inch scope. And that's why the image looks so much sharper and so much less noisy. Obviously, it's a smaller image scale. So when it comes to getting the details in some wisps here, yeah, you're going to give up that, if your skies are giving it to you in the first place, which they may or may not be. But that's then why F ratio matters. And so if I had an 8-inch f4, it would look the same exact size, sorry, if I had an f4 of that focal length, I should say, of whatever 8 inches times f5.75 is, I'm not going to do that math in my head, 44 inches or something like that. If I had that same thing at that focal length with an f4, it would have the same signal to noise as the bottom one there. It'd be nice and a heck of a lot smoother. Okay. So you can do that kind of thing. Also, of course, in telescope choice, there are things like the reflectivity of the mirrors or the transmission of the lenses. How big of a central obstruction do you have? I mean, yeah, maybe it's a really cool 12-inch astrograph running at f2, but almost all of that is covered by gigantic central obstruction. Well, the central obstruction is blocking a whole heck of a lot of photons. So at some point, you do need to factor that in. In some ways, that kind of thing is related also, or could be thought of or modeled at least the same way as the quantum efficiency. Different detectors that you have, that you can choose here, different detectors have different quantum efficiencies, or QEs. What QE is all it is it's the probability that a photon having hit the CCD well gets converted into an electron inside that CCD well, which then gets converted into a number inside of your camera and all this kind of thing, the intensity at that spot. So different CCDs, a lot of them, they just physically have different layouts. You'll have full frame transfer versus interline transfer CCDs, and they do these for different reasons. But full frame transfer CCDs are really nice in that, well, pretty much the whole surface there can be allocated to the actual wells that your photons are coming into. You can think of each CCD here as really basically being a bucket. And it's opened up to the world, and it's trying to say, okay, look, we're now trying to capture as many of these things as possible. And so you can make an array by sticking a whole bunch of these buckets all next to each other and then having drizzling down from space these photons. If your buckets are smaller, you're not going to catch as many of these raindrops. And sensors that have lower QEs typically have smaller buckets. All right, this happens because of things like they need to pack other electronics onto the wafer right there, which is a big deal with the interline transfers. They need to have separate registers right next to them to be able to quickly shift the charge over into them and then do a fast readout. But in any case, here, this is a simulated image. What I did is I took an image from the Hubble Space Telescope here of M51, used that as the ground truth, and in some of my simulators you can download it. It'll use an image like this to then try to show you the effect of these various things. But if we say, okay, look, if we model read noise, we model seeing, we model dark current and an exposure length and sky glow and all of this, on the far left might be what you would have with a QE of 1 kind of camera. You drop it to a QE of 0.6, and that's the kind of frame that you'd have. Because literally, you are getting 60% of the photons that you are for the one on the left. A QE of 0.4, you're getting 40% of them. So of course, your signal is going down. So if you're out camera shopping, pay attention to the QE. Pay attention to it a lot. Because if you start thinking about, all right, I'm not going to be able to image twice as much or image for half the amount of time because I've done something like double the QE as I move from camera to camera, that's a pretty big factor. Okay, so that kind of thing will help you actually boost up your signal. Each of those boost up your signal. Kinds of things that we can be doing to actually drop the noise. Now, in some ways, some of the things I've already been talking about, you can really think of as at the same time boosting the signal and also dropping the noise. But here what I'm really talking about is dropping the inherent noise. Not the noise in your entire stack, but really dropping the noise as it's actually coming into your camera here. And in all of this, really the take-home message is that sky glow is your absolute enemy. I get it here up in Irvine, you guys get it down in San Diego. I'm a little closer to LA than you guys are, so I probably get it a bit worse, but no matter what, we're both dealing with a whole bunch of sky glow here. What I've put up here is that same image of M51, and what I'm showing is using the simulator that I made, the effects of having either 2 electrons per arc second per second worth of sky glow, a nice, very dark rural kind of site, like you might find in Anza or something like that, or in Julian, versus what you'd have in an urban environment here with, say, 50 electrons per arc second per second worth of noise. It's the same underlying image. It's just polluted by the glow. And again, I can take out the expected value of the glow. I can know that, hey, the glow is pretty even in my image, so I could just subtract that off. Sure. But the problem is that glow has shot noise with it as well. And I don't know at every pixel exactly what that noise was. I don't know ahead of time how many heads and how many tails I flipped. And if I don't know that, I don't know what I should actually pull out. I know on average I should pull out something. Yeah, the average value of the sky glow. But there's still that noise that rides on top of it. And unless you're, omniscient, unless you're some god here who could know at each pixel exactly what was noise, you're not going to be able to pull that out. I don't have that ability. You can do things to try to smooth it. You can use noise reduction techniques in Photoshop or whatever. And all those are doing are those are just trying to say, okay, let me take a guess as to what the noise might have been and to actually pull that out. Let me give you not a visual, but now the sort of plot version of this. Again, when we say, okay, look, here's our target signal. There's the equation for the signal to noise. As we go and we start sliding the level of sky glow. So for example, I used some data here from Irvine, and I said, all right, now let me go and call my current sky glow 100% of my current sky glow. What would my images look like if I went to twice the sky glow that I have? And unfortunately, what you can see on here is you go from the middle of this plot to the far right of the plot. It's not actually changing all that much. It's getting worse, but not all that much. Whereas if I went to a spot that had 10% the sky glow that I would have, I've more than doubled my signal to noise. Oh, okay, yeah, no, I'll take that. And so that's then why your images are so much better when you get out of town and you go to a nice dark sky kind of site. Now, you can try to say, hey, look, that whole stacking thing that you were talking about before, Craig, that can actually be used to overcome this. And it's true. The math says that, yes, in fact, you would be able to overcome sky glow by just taking more frames. But remember these points of diminishing return? We were bumping into these same kinds of things here. It can start to become obscene amounts of imaging that actually required here. So our background sky glow can easily be 10 times higher in urban sites than it is in more rural kinds of sites. And so your shot noise is really dominating here. So here I've then drawn just two different SNR curves based on sort of number of images we would take, looking at them in Julian versus looking at it here in Irvine. And as you can see, if we pick something like we want to get to a signal to noise of 50 in Julian, you're talking, all right, well, that's about 12 frames or something like that. Well, actually, no, the math I did here to figure out the crossing point is that 12 frames in Julian equal to about 120 frames in Irvine. So, all right, I'm going to get a heck of a lot more data actually out of a place like Julian than I am here in Irvine. All right, so then you can start to do the math and try to figure out, is it worth the drive and setting up? You can also play the game of saying, you know what, but I can take an image every single night at home. All right, it may take me a couple of weeks to do what I can do within one night in a dark sky site, but that's just hard drive space, and hard drive space is cheap. So open yourself up to the possibility at some point of doing things like 500 frames or something like this. It's going to take that, but maybe in the end it'll actually be worth it. Okay, so dropping out sky glow is, for us, far and away the biggest thing that you can actually do to boost up your signal to noise. And there's another way you can actually do this, and that's to decide, all right, what I'm going to do is I'm actually going to shoot targets that I can filter out all of the noise before it even hits my CCD, or at least filter out 99% of it here. So this then comes to the idea of using line filters. So if you are in an urban environment, line filters are manna from heaven. What I'm showing here is just the spectrum here from a HA filter. This happens to be a Beta 7 nanometer HA filter. Yes, they differ and all this kind of thing, but for our present purposes, it doesn't matter a whole heck of a lot. So what we have is the standard visual spectrum down on the bottom, and then how much this HA filter is letting through that we actually see on the top there, just that one little red line. Now these days, our sky glow tends to be pretty broadband. There was a while, some number of decades ago, in which the sky glow, and in some portions, like near Palomar and this kind of thing, the sky glow is actually very narrow band because the lights in the area are very narrow band. But for most of us, sky glow these days is actually pretty darn broadband, which means that you can't stick some filter on there and hope to just filter out the sky glow. But for some targets, what you can do is you can say, all right, I'm going to let through the vast majority of the signal, and I'm going to then cut out all of the noise by using one of these line filters. So if you take something like an emission nebula, or I should say if you take not something like an emission nebula, if you take an emission nebula, what's going on here is that there are gases in the nebula that are emitting at very, very narrow lines. And so if you stick one of these filters on there, you may let through all the HA, you may, okay, you'll block out the HB and you'll block out the O3, so some of the signal has gone away, but at the same time, you've also filtered out almost all of the sky glow. The only sky glow that's coming in is the sky glow that happens to be at H alpha. And so you've done wonders to be able to actually pill out, let a whole heck of a lot less noise through. All that shot noise coming from the sky glow just went away. So here's a shot of mine. In fact, actually, those horsehead shots from before, those horsehead shots were all shot right here in Irvine. And those are actually individual, or actually very, very short stacks. This shot of the rosette here, also shot from my backyard here in Irvine. And it's a pretty nice kind of shot. It's got a nice signal to noise in it. And the entire reason is because it's, in fact, being done with line filters. And the way line filters work is you filter out all of that sky glow, so your signal to noise goes up. You've maybe blocked out, you've blocked out a bunch of your signal because you're only letting one line through at a time, but at the same time, you've blocked out 99.99 or whatever % actually of the noise. So here's another shot, actually of the whole sort of Orion swath here. This one was again taken in Irvine, and this one here, in fact, actually was, this is in fact 3 different panels. My sensor is square. This is 3 panels on a 4-inch scope. Each panel only has 8 frames at 5 minutes. So like the whole Horsehead, the whole Orion Nebula over there, all of that actually only comes from 40 minutes worth of data, period. So again, you can do, I mean, if a schmo like me can actually take something that looks pretty reasonable here, as I say, line filters are sort of manna from heaven for us. Line filters are going to do absolutely nothing for you on galaxies. Well, okay, fine, they'll let through a couple of knots and all this kind of thing, but you're not going to get a nice picture of a galaxy with it because galaxies are broadband targets. Reflection nebula are broadband targets. This trick works on emission nebulae. Okay, so we can do things like we can filter out the sky glow, or we can go to a place that has less sky glow here. We can also use a camera that has less inherent noise to it. So what I'm showing up here are images taken on the same night with the same exact telescope and everything. This is in a not actually a very dark environment here, but what I'm taking a look at here are how 4 different cameras actually do this same individual raw frame of M51. And you can see, I mean, look, the 2 on the left, all right, you can at least see the galaxy there. The one on the right, okay, I see the core, and I can squint and see a little bit of an arm, but that's about it. And so if you're using the camera on the, one of the cameras on the left there, you are going to get a better final picture than the camera on the right. I replicated this on another night just to be able to prove to people that yes, in fact, this is true and all this kind of thing. That's what we're showing on the bottom. A single 3-minute frame, again, showing, okay, what the whirlpool looks in each of these 2 kinds of things there.
Hey, Fred, what were the cameras that were used?
Since this is going up on YouTube, I'm not going to say. In fact, actually, there's another thing on the top versus on the bottom. On the top, the first 3 there are all actually mono CCDs, and the far right one is a digital SLR. On the bottom, so to pull out the color versus mono kind of thing, the bottom left is actually a 1-shot color CCD, and the bottom right is, again, a digital SLR there. Digital SLRs have their absolute strengths, no ifs, no ands, no buts, and these are older digital SLRs that were used in these. That said, they also have their drawbacks in that they weren't designed from the ground up to be something that is going to be open, have its shutter open for 5 minutes or something like that. And I've got some articles describing some of the issues that go on with there. So different cameras have different sort of noise profiles that you have here and different sort of inherent signal to noise. A chunk of it comes from the QE of the camera. Color ones are going to have worse signal to noise in these than monochrome ones. Think about how a color camera works. A color camera works by sticking filters over each pixel. Each pixel gets either a red, a green, or a blue filter. And let me tell you, they're not like, you know, super high efficiency filters. They're standard color dye filters. You may get 20% of the light to go through each one. That means you got 4 times as much light hitting the mono CCD than actually hitting the color one. That's why the luminance data doesn't look nearly as good. If you can have a luminance thing, it works a lot better. So you can see sort of one aspect of it. There's another aspect of it, and that is really what the noise looks like. What I'm showing you here is a bias frame taken from a particular camera here. And what I'm going to do is I'm now going to flip over and show you an immediately adjacent bias frame. Okay, so if I bounce back and forth between these, you can see, hopefully, I'll do it slowly so the video has a chance to kind of catch up. Each one of these looks like static on an old TV set. All right? And I don't see any patterns or whatever to this. It's just a classic kind of noise. And everything is going to have its noise. And the nice thing about this noise is that it's truly random. All right. Let me show you 2 bias frames taken from a different camera. Here's the first one, and there's the second one. First, second. People seeing the difference?
Yep.
Okay. In each one of these, you can see that there are, in fact, horizontal lines running through the image. So there's a pattern to the noise. However, if that pattern were always in the same spot, it would be fine, because it would be in all of our lights in the same spot, and it would be in our bias frames in the same spot, so we could pull it out. But the problem is it's in a different spot each time. So that is, again, this noise. If you can't know where the lines were, you can't know where to pull them out of your image. On the first frame of your lights, maybe they were here, and on the next frame they were here. So how do you know which one to pull out? You don't. And that's then the problem. If your camera is always repeatable, that's fine. If it has noise, it's fine so long as the noise is random. But when the noise has a pattern to it and that pattern moves, now you got a big problem. So that as you start stacking these images on top of each other, eventually it may finally average itself out, but it's going to take a long time for that to happen. And all the while, you'll then have these splotches or these lines or these blobs or whatever it ends up being. That'll be in the background of your image. You stretch and stretch and stretch to try to actually find that nice faint bit, that nice faint galaxy in there, and oh, I've now hit the cruddy part. And I don't want my background to look like crud, so I've got to back off. All right. Another way we can sort of try to look at this instead of just toggling back and forth is to use something called a fast Fourier transform, or FFT. And in a fast Fourier transform, what it does is it turns the image into frequency and phase components. Now, okay, we don't need to get into the details on all of this, but what is good to know is it turns this image into, well, let's think about these frequency components. Every image has some average value. It's got some average level of gray or whatever that's in this. That's represented by the very center of each one of these plots here. So if you notice in each one of these, in the middle, there's actually a little bit of a bright spot or dot. It's called the DC offset in this fast Fourier transform. Higher frequencies, fast little changes in everything in your image, they then move out from the center, both horizontally and vertically. I'm saying all of this because really camera number 1 here is pretty much an ideal FFT from your bias image or from your read noise image. What this is showing is that, you know what? There's an average value in the read noise frame. And then there's some random stuff scattered around, but nothing that you actually are ever going to pick out here because it's just a bit of randomness and there's always some noise. Camera 2 looks pretty darn good. It's got a little vertical line right there, which means that there's a little bit of horizontal fixed patterns in this. Camera 3, these are all stretched the same way. Okay, it's got that, and it's got more noise overall than the other two, but it's still okay, not too bad. Camera 4 looks not too off of camera 3. Camera 5 and 6, however, we're now getting a whole bunch of other stuff in here. And that stuff are things like these lines that move from image to image. And that's what you're now going to have a tough time as you're stretching and processing, trying to pull it out. All of this, by the way, if you want, I can cover it in another session. It's also covered in my Cloudy Nights bits that you can get to in terms of how to even just take some of your own bias frames and make these plots in free software out there called like ImageJ. Okay, so I started off all of this by saying, okay, that there were two simple ways you could actually improve your signal to noise. You could boost your signal, or you could drop your noise, but by boosting the signal, we can do things. We can stack more frames. We can expose each image longer. We can lower our F ratio to actually get more photons coming from the sky to hit each thing. We can use a higher QE camera to convert more of those photons into electrons. We can, of course, also drop our noise. We can reduce the sky glow, by actually going to dark sites or by using filters. And we can also use a lower or better noise kind of camera. All right, so I've been talking here pretty non-stop here for about an hour here, but I want to then open it up to everybody for some questions.
This is Dave. I use kind of an anomaly for imaging. I've got a one-shot color CCD.
Mm-hmm.
Is there? I know there's no magic formula, but I've always, and of course the resultant lowering of QE because of the Bayer filter on top of the thing.
Yep.
The chip the chip was out of it's an STL 4000 XEM, which uses the chip out of the STL series.
Mm-hmm.
How I've always said, okay, you can overcome the loss of QE by taking more images to be able to overcome that. Is there any type of formula that says you take X amount more, or you take a lot more, or you just take 30% more?
Yeah.
What's the effective loss of QE when you put a Bayer matrix on a chip?
So the first thing that you need to, by the way, are you seeing me or my screen right now?
To you.
Okay. The first thing that you need to do is you can take a look actually at the spec sheet for your sensor. And on that, you're going to actually be able to see, relative to the monochrome QE line, you're going to get a QE line for each of the 3 different colored pixels. And what you're going to want to do then is you're going to want to be able to either visually or by putting it into some graphics program and kind of tracing it out, try to get an estimate as to how much area those different color curves have relative to the entire thing that you would actually be getting from the luminance channel. And if you say, all right, it may very well end up being that each one, for example, has a quarter the area that the clear filter would actually have. So what you now know is you've said, okay, look, my target signal is now 25% what it would be if I actually had a straight up luminance kind of thing. Now then, my shot noise from this, has gone down a little bit as well, but I'm running 25% of it. Or the other way you can think of it is you've quadrupled the signal that we actually have coming from, by going up to the luminance kind of thing. And by quadrupling, you've now basically doubled your signal to noise. In fact, I believe I have some, from another talk, I have that exact demonstration that I tried to show some folks. And this is what actually makes, excuse me just a second, this is then what makes the LRGB imaging technique often so incredibly powerful. Because by doing LRGB, you get to then have this luminance frame that's getting, call it about 4 times as many photons to come through. So let me just try to, yeah, here we go. Let me now just tell you to share the whole screen. Let's do the whole screen share and hit here. Okay, so here's what this kind of thing looks like. If you don't know the concept of LRGB, you can say that, all right, here are two images. These are beautiful Hubble images, and they come from Hubble site, so I can put them up here. And you can see that, all right, we can have a color sort of aspect to this, but we can extract out of that color just the raw intensity here. And I can take this image, I can take the color component, the RGB image, and I can start blurring it and blurring it and blurring it to reduce the overall resolution in it. And the cool thing is, if I layer the luminance back on top of this, all right, fine. By the time I've gotten all the way over to this super blurry one in the lower right, and now I layer the luminance on it, you can tell the difference between, say, the upper left and the lower right. But really, as you're looking like the upper left versus the upper right, oh, I can't spot a darn bit of difference actually between these images. The color looks exactly the same on it. And yet I have a much blurrier, lower resolution kind of color in those frames. So okay, if we say that, all right, here's what I'm going to do. I'm going to take straight RGB imaging, and I'm going to say, okay, look, I'm going to do, have 200 minutes or so worth of red versus and green and blue, how many photons in each and everything I get out. What we can actually do is we can say, if I were to combine these and create a synthetic luminance from it, this is the luminance, this is the signal to noise I would get. Each one of these 7.75s combined becomes a 13.4. Now in the one-shot color, it's a little different in that for the 200 minutes worth, you're getting that one individual, you're getting that complete, kind of data here. But if you then just say, all right, instead what I'm going to do is I'm going to do an LRGB kind of technique, you can see then that, all right, you are now getting a nice big boost here in the signal to noise in your luminance frames. And if you go even further here and you say, okay, look, I'm not going to spread things out nearly as much. I'm going to do 2-to-1 luminance versus the RGB, your signal to noise goes even higher. And so if you say, all right, what do I have with one frame at 30 seconds versus 20-second RGB frames and sticking them together, and you reconstruct a luminance frame, this is the kind of thing that you can actually pull out of it. Now, as I say, that's when you're doing a straight-up color camera happening at doing RGB versus doing LRGB, but a lot of the same applies. We do have to factor in the notion that you get all three of them at once. And so, there decidedly is that. So, okay, that unfortunately ended up being a long and roundabout way to saying I still actually apparently have to run the math to come up with the exact answer for you because of that issue that you're getting them all at once. Sorry. Because, I mean, Dave, when you think about it, since you are getting all three of them, yes, your luminance then has less SNR in it because you have, say, 20% of the photons going through. However, you don't need, I mean, if we all want a color image at the end, you don't need to take separate red, green, and blue images. You already have them. Whereas on the mono camera, I do need to take them. There have been some nice empirical demonstrations even on this. I'm going to have to get back to you with a link actually on that afterwards. I'm trying to remember right now who did it several years ago. Took two S-Big cameras, the the mono, and did LRGB imaging and did the one-shot color and did the one-shot color imaging kind of thing, and then was able to show the straight-up difference between them.
Yeah, I actually have that article. I read that quite like 4 times before.
Yeah.
I thought, okay, I'm going to go take the dive and go get the 4,000.
Yeah.
He had some really remarkable results saying, yeah, you take a hit, but it's not near as much as what you think.
Exactly.
And his end result was, if you're going to do that, then make sure you take 20%, 30% more pictures, and you'll sort of get there, sort of type of thing. So,
right.
The other thing he says, geez, I think the end result of that particular paper was that I'm going to keep both of these cameras because what I'll do is I'll take luminance and I'll shortcut the whole thing by using the color camera to take the RGB components and to put them all together.
And that actually is a phenomenal look. I mean, if you can sort of afford to have the two cameras here, that's a fantastic way to go about actually doing this. Yeah, all right, fine. Your RGB data and everything, you can run binned on a mono camera and all this kind of thing. It's so nice to have them perfectly registered. It's so nice to just be able to say, okay, look, I'm just going to set it up and go, and then get all of your color data out of that, get your luminance out of the mono, maybe even blend in a little bit of synthetic luminance. You got it, you might as well. Blend in a little bit of that kind of thing, and yeah, you're in nice shape. So I should at some point actually though run the numbers to really figure out what the true difference is there.
I'll email you the specs on the chip, what's going on there. But because SBake still has the data up available on that particular chip. So the other thing, the curve that you showed versus time, where both curves are asymptotic. You were showing as far as images reducing the noise as far as the amount of images. You also showed a curve that showed that one right there, more images. The other side of the curve, the inverse of the curve was time.
Right.
That one right there. So, in your estimate, and I know I've talked with some other folks, Tony Hallis and Ken Crawford, about what is the magic point? Is there such thing that says, given what your sky glow is, and let's say you put a sky quality meter up there and you're 21.5 or something like that. Given that measurement, is there a way to determine the best amount, at what point where you're wasting your time? It is, do you take 25 shots of 10 minutes apiece? Have you made a calculator, or is there somebody that makes a calculator that says what is the optimal? And I back up a little bit, because Greg Bricklaw has a very, very powerful image calculator built into SkyTools 3, yet even he says, this is Rev 1 on this thing, and if you play around with the exposure settings on as far as the filling in the fields, the signal to noise ratio doesn't seem to, matter of fact, it doesn't move at all if you're playing around games with time, with exposure time versus the amount.
Right. So
go ahead.
There are a couple things in here. First off, you don't actually need a sky quality meter to be able to measure these things. If you have a patch of dark, where there isn't nebula or galaxy, that's your sky glow. You can say, all right, look, here I'm reading out of my image, and I'm getting 1,000 in the background here. Let me take the bias frame, or let me take a dark frame of that same duration. Okay, in the dark frame, it's at 100. So, okay, I now know that the total sky glow here is 1,000 minus 100, or 900 ADU in that time. Let's say it was a minute-long exposure. So it's 900 ADU per minute is my sky glow. Move over into a spot here in the nebula. How bright is that? 1,020. Okay, so now it's 20, because of the difference between my sky glow and my nebula. 20 ADU per minute is coming actually from my target. Cool. So you can extract these kinds of numbers from any of the images that any of you already have. And so the calculator that I put together lets you go through and say, okay, let me see if I can just make this a little bit bigger for folks. And I can even, in fact, just share.
You can share the app, you just don't get
exactly.
It. Yeah.
So here, what this shows is it says, okay, look, what is the sky glow background? 32,095. All right, what's the target signal, the ADU of your target? Pick some spot in there. Of course, it's going to vary a little bit, but pick a representative kind of spot that you care about. All right, there it is. How much is the dark signal in a match dark frame? How much is coming through in a bias frame? How long was your exposure duration? And then it goes through and it figures out, okay, how much total signal is there? How much shot noise is there? How much total noise is there? What's your SNR in this kind of thing? And you can then start to say, okay, what would happen if I changed some of these numbers? What would happen if I changed the dark signal? And start to then play with these kinds of things. This also has a chart that goes through and talks about the effect actually of sky glow in this. Percent change in sky glow from where you are. There's a thing that goes and calculates what would happen if I changed the single frame exposure duration. So it's worth noting, however, that the two curves that I showed before are not contradicting each other at all. In the first one, where you were seeing that the signal to noise was going down and down and down with more and more frames, that's also saying how much time you're spending on that target. By adding more frames, you're adding more time actually on that target. The second one is then saying, okay, I've already said I'm only going to be doing an hour or 6 hours or 100 hours or whatever it may be on that target. How should I divvy that up? Now, in terms of, there is no point of no return. At every point, there's a point of diminishing returns, and it's up to you to figure out what the trade-off is here. Let's say that your mount is absolutely perfect. It never errs, it never moves by more than 1/10 of an arc second, and there are never any airplanes. Okay, you know what? In that case, and if you don't have like a lot of fixed pattern noise, you want dither to get you around or whatever, you know what? Open it once, leave it open for 6 hours, close it and you're done. So long as you don't saturate and all this kind of thing, sure. All right, well, you are going to saturate at some point. At what point? Well, that's going to depend upon the individual things in your camera. Where does your camera saturate? So that's going to dictate things. Your mount is going to have errors at some point. I know on my rig I can reliably pull 5-minute or so exposures. I start going beyond that. Okay, I can get 10 a good amount of the time and this kind of thing, sure. But on another mount, the one I just took to Julian, no, I can't pull 10-minute exposures. It's an inexpensive mount. So I'd be throwing away all of my data. In the end, I might have 10 minutes worth of data for the whole night. Okay, let's not do that. But I can get it to go for 2 minutes just fine. So the answer to this, unfortunately, is going to depend upon the rest of your conditions and your gear. What you can do, though, is you can say, how much am I giving up? How much am I losing by only imaging for an hour, by only doing a minute or a 2-minute exposure and this kind of thing?
Hey, Craig, is this spreadsheet available on your site? Or?
Yeah, yep.
Cool.
So in fact, if you go to starklabs.com, there's a section there for articles. And in the articles section here, you can get to PDFs of all of the reprints of the Cloudy Nights things. And then you can also get to the spreadsheet here.
I can show you guys after we're done where that's at. I've been up there quite a bit. Just, you know, I kind of cheat. I've got an AO sitting on my system, and I can basically tell it to run from, you know, from 1 minute to 60. It doesn't make any difference. It's the AO is taking, you know, basically taking care of anything that me decided to throw crap-wise into my mount. So I've got the ability to take as long a picture as I want, given what, you know, given.
But when you do that, in particular, since you're getting your luminance and your color at the same time, if you took a 60-minute long exposure, almost all your stars would be white because they would have saturated, and they'd be flat discs.
I tried that trick as well, and it doesn't. It's not very spectacular, other than the fact that you can guide for an hour.
Exactly.
It's, you know, I've been playing around at our dark sky site. I've been playing around with imaging, you know, in the 15 to 20 minute range or something like that, depending on what it is I'm poking around at. But I've never found an ideal spot. It was kind of, everybody says yes, and by golly, well, I think I found it this much. And well,
in that case there, your answer is a pretty simple one. If guiding isn't a problem at all, and if satellites and planes aren't a problem at all, those aren't constraints, those aren't costs by going longer. You still, though, have the cost of going longer of then saturating out your stars, and so you lose color, or blowing out the center of a galaxy, or something like this. So that then is your cost. The answer is go as long as you can before that cost becomes a problem.
Adaptive optics. It makes everything in the meat mount a whole lot better. No, what it really does is it's a small glass element that's moving very quickly, in some place in the neighborhood of 8 to 12 frames a second. And what it does is it shifts in relationship to what a guide star is doing. It actually is a full active feedback loop, and what it's doing is it's moving this little glass element very quickly. So if the wind blows or the mount does something, this thing takes up for it real fast. It's much, much faster than the standard guiding.
Hey, Greg?
Yeah.
Something you didn't really emphasize here is fixed pattern noise and in the CCD and using dithering
Yeah.
to compensate for it.
Yeah. So I mean that comes a little bit under the sort of heading of the quality here. If you do have a fixed, if a noise is truly fixed, in that it's just being added in, well, of course you can subtract it out. Most of the time, however, these, the quote fixed pattern noise, they're either noise components that are fixed, and so it's always adding sort of random bits or whatever in that spot, or it's actually still a little bit variable. To overcome either of these, well, your best bet, as was mentioned here, is to use dither to try to actually get it so it will average out. So I just saw a talk at SEAE by Tony Hallis where he was showing some really beautiful DSLR images, and his trick was to make sure that he moved between frames enough so that he was sliding out of the size of the fixed pattern noise. So on his camera, on his Canon, it was on the order, he called it about, talking in terms of sky diameters, but he was really talking on the order of moving at least 10 or so, if not more, pixels between frames. So where you have a spot that in the background, it's just blue, and it's blue in all of the images, because there's a little bit of a bias there just to be blue. All right, yeah, that's the case, but now if you slide over onto another patch of sky that, most of the time it's red. You do it again. Another time, most of the time, it's green. And you just bounce around and bounce around here, you're getting these on average to cancel each other out. And so you end up then in the end with a pretty neutral looking background, pretty neutral looking sky. Dither is another option here then for what it's doing is it's whether it's coming from a fixed pattern deep in the sort of the noise in the background of your digital SLR, or whether it's coming from things like hot pixels on your CCD or on your digital SLR. By moving them from frame to frame, it's a lot easier to pull them out. You can either have straight up averaging take care of it, the way Tony was doing with that background fixed pattern noise, or when it comes to things like hot pixels, I talked about in my last talk, I talked about using a different combination method, the standard deviation or sigma clipping kind of combine, that says anything that seems like it's an outlier that's not kind of near the other values, throw that away. You can get that if you have motion in between your frames. So that, yes, by the time you've lined up all of the same stars on top of each other, you've now moved the hot pixel to different locations across the image. And so it always jumps out as a, hey, this is a totally different kind of thing here. And so it's easy then to get that to go away.
In nebulosity, you have, when it's coupled with PhD, you have different settings in terms of the dither.
Yeah.
Guidance as to how to choose those settings?
Again, this is going to come down to some of the things having to do with your own camera. If you're really trying to deal with the big blocky noise that a lot of SLRs actually get, then you want to have a whole bunch of dither. If you're just talking about being able to get it so that the hot pixel doesn't line up, well, moving by a pixel or two is going to be able to deal with it. The way the dither works in PhD is the control program, be it nebulosity or something else, tells PhD to do a move of size X, and there are a number of choices in there. PhD then says, all right, I'm going to take the current lock position, and I'm going to add or subtract a random number scaled by X in here, and that's my new lock position. It then starts moving the mount to get it so that the star is now on that lock position. All the while, the control program is saying, are you there? Are you there? Are you there? And once a threshold is reached, in terms of saying, yes, in fact, I'm here, PhD says yes, and then nebulosity or the other program goes on and takes the next image. So in all of this, though, you should also be thinking about how much motion on your guide camera means how much motion on your main camera. So let's say that you want to have a whole bunch of motion on your main image, and you're guiding through the same telescope. You're using an off-axis guider. Well, if you want to have 20 pixels worth of motion on your main image, you better have 20 pixel motion on your guider, because they're the same image scale here. If instead you're doing something like you're saying, okay, look, I've got a really short focal length guider. I'm using a finder scope as my guider. moving by 2 or 3 pixels on there would equal 20 pixels on your main one. So you need to keep this kind of balance and everything in mind. You know, for me, the kinds of imaging I do, I'm trying to get away from the hot pixels and that sort of thing, and so I just have it go a couple of pixels here and there. The more you have it shift from frame to frame, the more you're going to lose in your big final stack. Because your final image, when you've aligned all these on top of each other, it's going to be the amount of image that's there in all of the frames, because you'll get those fuzzy borders or black edges and this kind of thing that you can see when you line things up where there's been a lot of motion in between the frames. By the way, little trick, kind of the skeleton in the closet. If you're guiding, if your guide rig and your main rig has a little bit of differential flex, you don't actually probably need to dither. It's a fun little trick.
Absolutely, yes.
It works like a charm. You know, just loosen the brackets on your guide rig a little bit there. You're going to induce this flex. The easy way to see this is, I mean, if you take a program like PhD, and if you watch and that star stays on the crosshair all night, or maybe it bops off by a little bit and then comes back, and it stays there, your guiding is fine. The guide camera is keeping the star in the right spot. If the crosshair is here and the star does this overnight, okay, you got a real problem, and then there's something going wrong in your guiding. But if it stays on here and maybe just bounces around but keeps coming back to that, your guiding is fine. Now then, take a look at your actual subs from the night. Even just thumb through them. PhD has a preview tool that you can just go through and take a look at them. And if they keep marching, dung, dung, across the night, you have differential flex. Because the guide camera kept your mount, according to that guide scope, perfect. And anything else that's moving has to be because there's some flex in the system. That's the only way it can actually happen.
Yep.
So you could use it, though, to your advantage and say, hey, look, this is dither. And what you should then probably do is have your camera rotated a little bit to it so that it's dithering on a diagonal. So easy, quick way of getting dither. Have a flexy kind of setup.
Craig, I have a question about the comments you were making about F ratio.
Yeah.
Another way of saying that if you are limited for your exposure time, you should be seeking a higher arc second per pixel.
If you get, it depends on how you get that higher arc second per pixel. If you get that higher arc second per pixel by, well, yes, okay, yes, no, you should be saying that. Sorry, it took me a second there, but yes. Because what you're really saying is that the F ratio is saying how much of a swath, the arc second per pixel kind of thing that you're actually getting, you know, then out of that. And so, yes, that's what you should be aiming for. And I mean, you'll get that then by sticking a focal reducer on there or something like that. You can also get bigger pixels. You know, that ends up doing the same kind of thing by saying, okay, look, I'm now going to get more photons from that swath of sky to go and actually hit.
How closely does binning follow that model? I mean, it's if you've got, you know, basically if you're jumping from a 7 micron, if you bin a camera that's got 7 micron pixels so that it effectively becomes 14,
yep.
Is it really effectively 14, or is it mathematically put it together? How does binning?
No, it really is, because when you take a full frame transfer CCD, full frame transfer CCDs have their pixels really just butted up right next to them. So you can think of it as, hey, look, it's this great one that's physically twice as big. The interline transfer ones will have things then like this, where you're going to have 2 pixels and there's a gap in between them. But still, ending up, it's not actually acting like one that was this big, but it's still ending up acting as one that was twice as big in this direction and twice as big in the other direction as well. It's just that each one started off as a smaller kind of thing. So you are getting, by binning, you are getting 4 times as many pixels to hit that, and you're also getting just one of the read noise elements. Because when the binning is happening on the chip, not when it's happening in software, when it's actually happening on your CCD chip, it combines all of the electrons from those before it goes and hits the readout. So you're getting that same kind of thing of getting 4 times as many photons to hit it. And you've also then done the same thing of losing some spatial resolution, just as you would have by dropping your, by dropping your focal length, and therefore dropping your f ratio with a reducer. So yeah, no, they're going to end up being the same kind of thing.
All right, my favorite part last time, no offense, was your workbench. What cool goodies you got there? It's off camera.
Oh, unfortunately, my workbench even got cleaned up, which is kind of horrific here for me. But there are still plenty of goodies in here. So they're probably unfortunately the same ones as before. But somebody actually asked last time though about my thoughts on the QHY. And in fact, I was just out at the Julian Starfest, and I know I saw at least one person from the club there that I recognized from last time. And I went out and I shot with the QHY-10, doing one-shot color and sort of like a nice area in Sagittarius and all that kind of thing. I had my nice QSI 540 and everything with me, but I wanted the convenience of the one-shot color, not having to deal with scripting and combining and everything that night. I wanted the nice big honkin' chip that you get out and everything on there. So I took that with me, and that's actually why that goodie is even downstairs. But yeah, downstairs there's a Starlight Express. There are, actually some different goodies I could show you. You wanted the boxes of cameras?
Yeah.
More cameras. There's a QHY-9, a QHY-8 Pro, a QHY filter wheel. There's the QHY-10. So as you can see, there are a good number of random cameras around, various prototypes, early ones, more modern ones. Here's a, you want some guiders? Here's a CCD Labs QHY-5. Here's a QHY-5-2. Here's a Orion version of it. Another version of it.
I hate you.
and this is about half of them. So.
Did you camp overnight at Starfest? Did you stay out for?
Yeah. So I went out on Saturday night with my oldest son. Camped out there. Brought my little 4-inch Borg. Brought a little Ioptron ZEQ 25 mount that I picked up from OPT a couple months or so back, and that was actually the first time. The first time I've actually been able to collect photons from something other than the wall back there. In a long time. So it's been quite some time. But I was actually able to get an image. I haven't finished processing yet. I'm going to sit down with my son and actually do a lot of the processing and stretching and try to pull it out into a nice image we'll print up and stick on his wall and stick on my office wall and that sort of thing.
Did you have lots of visitors asking you about your imaging and all that good stuff?
I was set up in an area where everybody was straight visual. Seems as if a lot of the folks set up there were sort of straight visual, and so it was like, oh, you have a camera on there?
I found it just the opposite. I was trying to image, and every time I'd start something up, I'd have 5 or 10 people standing behind me going, oh, is that a Mullen cam? No. Woody was very popular with his live setup there in the tent.
Right.
And people
I thought of having a nice kind of live setup, but I was having all sorts of, when you haven't done it for a couple years and you're now doing it on gear that you've never actually used, there were a couple little technical challenges along the way, but we got images. It worked. There's definitely something in there. And
what do you think?
My go-tos were all off, and I was shooting something that I didn't know, and I didn't do it the smart way.
Been there,
Sound
done
familiar?
that.
Yeah. But hey, the guiding was spot on.
Yeah, what program did you use to guide?
No, I used PhD2, and I'd done a little bit of work with PhD2 just in the backyard here to try to sort of check out the new mount, and there actually was a mechanical issue. I had to swap one of the gears on the mount. But in any case, that was the first time I'd used PhD2 to actually make an image. Obviously, I've made tons of images with PhD1, but PhD2 has been a really, really fun thing for me. I mean, way back, it was, I don't know, like a decade or so ago now, I had the idea for PhD. I was frustrated with guiding packages at the time, in that I didn't have any kind of thing I could set up and leave set up. I would have to trek out to some site that was only badly light polluted instead of horribly light polluted. And I would set up, it would be late, it's either cold or I'm getting eaten alive by mosquitoes. And bless them, Guide Dog would be able to guide well if you could enter in the 57 parameters that it wanted to know, but I couldn't remember, is this rig east-west flipped or north-south flipped or not flipped at all, and how many arc seconds per pixel, and I couldn't remember and enter in the right values each time. And so I sat down and I said, it's like, okay, look, computers should be able to figure this out for you. You should be able to have something that's smart, that can figure out all of these parameters, and yet at the same time be push here dummy kind of simple, because at midnight I'm an idiot, and so I just want to be able to hit go. During the daytime I can figure out what all these things should be, so I'll write the code to be able to do that. And so then I had all these grandiose ideas as to what PhD would be able to have, and then after I wrote it and I put out an early version of it, these guys in this EQ mod group in Australia started putting up these images off of Atlas mounts that were going for 5 minutes and 10 minutes and taking these beautiful pictures that were better guiding than I could get out of it. And so I was like, okay, it's working. And so I then at that point started saying, all right, I want to support more cameras, I want to support more mounts, but the basic guiding routines and everything, well, they stayed. I added in a couple things to be able to have some different automatic declination routines, but the core guiding routines hadn't changed, and the core code base hadn't changed. And at the same time, the world has moved, and a lot of people started using PhD, and I tried to have it be something that was easy and simple to use, but still there were always, could it do this? Could it do that? And it's like, it could. I'm a professor by day, and I've got this other software, and I've got a family, and yeah, that's a lot of time to keep putting into this. And so this guy Brett McKee came along and said, you know what, it's great that you've released this. I released it as open source, so there could be a Linux version of it. He said, I'm a professional programmer, and your code is good, but I'm a professional programmer, and I'm a stickler for clean code, and would you mind if I rewrote it all? And, well, no, go for it. Because in rewriting it all, he set it up such that a whole big group, an international group, could actually decide, you know what, we're going to add these other features in, we're going to do this. And then by having that whole crew working on it, all sorts of things that it's been dying to have for years could actually be added, things that I just didn't have time as a single programmer, I didn't have time to be able to do myself. So it's this odd thing in that I don't know immediately how to program actually for PhD2, because the code base has totally evolved and changed since I wrote PhD1. But the great thing is, by having this crew, we all share a common repository, and if I make some change into PhD1, if I do something like add in support for a new camera or tweak a bug or something like that, I've had times where I've said the next morning, okay, you know what, I'm going to put this into PhD2 myself. I'm going to get credit for actually committing something into the new software base. I call up the software repository and I see that 6 hours ago some guy in Australia already took care of it. On the one hand, I sort of groan, like, geez, I don't even get to add that into PhD2. On the other hand, it's fantastic. Because here there is a group of people dedicated to it who collectively have so much more time than I do and are willing to make it the product that it actually is. And so it was really then fun for me to actually be out there at a Starfest, not giving a talk, just being a user, camping out, and even using software that in some ways technically I didn't write, which was a little bit strange, but was very, very good nonetheless. I still obviously knew my way around it. The interface and everything is the same. The core algorithms and everything are the same. They've added in wonderful bits. How those algorithms are written up is what they've changed to get it so that you don't need to spend a week staring at my code and digesting my idiosyncratic kind of way of doing things to be able to get it. It's much better set up now than it was before. So are there any other kind of questions on things?
Well, good here.
Hey, Greg, what mount did you say you were using
So that's an IOPT. So my main mount that I have here is it's a Losmandy G11 Gemini 1, and it's great. I've got that mount dialed in. In fact, it came from the factory dialed in nicely. I didn't have any of that 76-second periodic error. It's a great worm. The go-tos on it are fantastic, but the thing is big. And to carry, I mean, my entire imaging rig, telescope plus camera, even the heavy camera, comes in at 12 pounds. It's massive overkill. And so I wanted to have something that I could actually take with me. On a trip like this, or when I go with the family, I go somewhere and it's dark. And so I picked up one of the iOptron ZEQ 25s. There are some really nice bits of data and everything on cloudy nights about it. Picked it up from OPT. They were really, really great about it so that I could swing on down and pick one up. And it's a nice mount. It's a really nice mount. I did have an issue with it initially. One of the gears was actually malformed. They've got a little aluminum gear inside there, and I'm going to post this up at some point on cloudy nights so folks can see. But the set screw goes through the teeth, and they punched it in too deeply, and they also put it in a little bit wrong spot. So the upshot was that there was a nice little gap on the gear, and so as a belt went along, it could slip. So every 20 minutes, I would jump by like 40 arc seconds. And so I was like, okay, that's a problem.
The worm gear you're talking about, or the main?
No, it's not the worm. It's one of the things that then ends up driving the worm. So you've got the motor that's got its own gear reduction box. It drives a little aluminum gear, and it was that guy, which then has a belt which goes to another aluminum gear, which then goes to the worm. Overall, it's a really nice little mount. I like the way it's set up.
Have you seen any problems with the worm itself in guiding?
No, in fact, I've of course got two worms because there's one, it's the same one on RA and on deck, and the one I've got on the RA one right now is a pretty nice smooth worm. So total error on it is not bad at all, and it's nice and smooth. So at least what I was doing when I was running some tests here, you know, it would be going plus or minus maybe 10 arc seconds or something like that, nice and smooth. Then there was this huge jump, and then it'd be nice and smooth, and then a huge jump. I now have all those huge jumps gone. It was a problem unique to my mount. I hadn't seen anybody else describe it. iOptron tech support was great. They hadn't seen this happen, so I think it was just an isolated incident. I mean, seriously, was that when somebody pulled down, you know, to put the set screw in, pulled down on the drill press, they just went down too far, and so then the chamfer on the setup ended up taking out too much material, and that was it. They shipped me out a new one. I put it on. Took 5 minutes to swap it in place. Now the mount's running great. I got to figure out how to get my go-to spot on with it, but that's user error, not their error, I'm pretty sure.
iOptron there's a hand there. Look out, there's a hand.
We have a hand in the picture.
Oh, you got a hand in the picture back there, yes. My older son's now famous hand.
iOptron has a new mount. There he is.
Hi there.
That's the one that was at the Starfest.
iOptron has a new mount, the CEM60.
Yeah.
Opinion on that?
I haven't seen it firsthand or anything yet. It looks pretty cool. I'm really happy with the fact that somebody has decided to rethink mounts for us. Because, I mean, when I first got into this, when I was like my son's age there, you know, I had this book, like the Standard Handbook of Telescope Making, and it described a German equatorial mount, and it described a fork mount, and you know what? It's been, you know, 3-4 decades or whatever. It's probably been at least 4 decades since that book was published. why hasn't anyone thought of a cooler way to do a mount for us? So it's been neat to then see in the last 5 years or so a number of makers decide, you know what, let's rethink the mount. So whether it's something like let's put encoders here on the axis, or let's have basically what ends up being a robotic arm, really, really expensive, but, another way of doing it, or the Ioptron Z setup, or their other sort of just integral thing of saying, okay, let's figure out ways of making it still serve the purpose, but solve this problem in a little bit different way. So I didn't need the 60 because I have a nice, weight capacity carrying mount in my G11. My G11 can carry a whole bunch of weight, far more than I ever have to throw on it. I needed a small, light, kind of thing. I decided against the sky tracker kinds of things because I wanted GoTo, because I have no idea where anything is in the sky, it seems. So I went that route. And I didn't. I used to have a TAC EM10 GoTo. Oh, that was a sweet little mount. It had its arcane bits and all this kind of thing. No planetarium software seemed to, support it almost, but it was really, really smooth. It lined up really well, but at one point I sold it on cloudy nights or something like that to somebody to raise some cash or something, and kicked myself afterwards, but whatever. Yeah, but so far I'm really happy with the Ioptron setups. It seems as if any issues that they'd had early on in terms of trying to, be able to get their production levels up and everything seem to be done, and they're putting out some really fun kind of mounts.
Is that it, guys?
Yep.
All right, great. Thank you very much for filling in. I really appreciate it. On such
Sure thing. Well, hopefully you get. So is Ken going to be rescheduled for another night for you guys?
Yeah, we're good. He's committed to the 24th next month. So.
Excellent. Ken gives a fantastic talk and makes images that are so many orders of magnitude better than mine, it's ridiculous.
So, all right. Thank you very much. Have a good night.
Excellent. Take care.
Thank you.